I'm from Team Ukraine, and today I'm going to report our solution of problem number 8, candle lighting. The problem asks us to study the possibility of relighting the candle from the maximal distance by burning the vaporized wax. And here you can see that indeed it can be done. Sometime after the flame was extinguished, the vaporized wax go upward, and if some region is ignited, flame spread down. So we have upward convective flow versus downward flame spreading. And the natural condition for lighting to be possible is that the flame should spread faster than the convective flow takes upward. But is this obvious condition sufficient? As we perform first experiments, we understand the wisp of smoke is very curvy, which is due to the turbulences in the wisp and around the wisp. And even in a lower stage region, its width inevitably disperses due to the diffusion. The important process is the cooling of the wisp of smoke. The higher is the point of the wisp of smoke, the lower its temperature. So all this limits the possibility of relighting. And now, as we know the mechanism of phenomena, we move on to theoretical study its limits, and then in experimental part we propose our experimental setup and find the maximal distance, and it's dependent on different parameters. Let me start with first condition on the velocity. To investigate the flame of propagation speed, we first introduce the characteristic size of burning region, and from the flame thermodynamics, it's of order of square root of characteristic time of burning reaction. And for realistic parameters, the velocity of flame is more than 1 meter per second. And in other hand, we have convective flow rate, and we can estimate it from balance of buoyancy force and viscosity force. And for realistic parameter, we obtain that it's sufficiently lower than velocity of flame spreading. And to check it, we direct the wisp of smoke and obtain good correlation with our estimation. And as for the velocity of flame spreading, we obtain that it's indeed sometimes greater. And we understand that the first conditions for the lighting to be possible means for our parameter, our problem. Now we move on to the thermodynamics of the wisp dispersion. And to ignition can be possible, should be the temperature of vaporized wax should be high enough, and to further sustain of burning reactions, some lower temperature is enough. We consider that the ignition condition are fulfilled by a lighter flame, and we also understand that concentration of the wax vapors and temperature should be high enough for sustained burning. And this condition we can obtain from the consideration that heat produced by the burning of the wax vapor should exceed the heat needed to raise the temperature of the new portion of the wax up to the burning temperature. And so we obtain the combined condition on the temperature and the concentration of the wax. So we have to study how these two parameters change with the height above the candle. And to do this, we can characterize the angle of dispersion phi and wrote the law of pressure decrease with the height. Also, we understand that ignition is limited by even lower height, where the turbulences break break the steady upward flow. The dissipation of wax vapors is highly important in our problem, and so we will simulate it. And we simulated in problem which my team member wrote, and from this simulation we obtain the dependence of the wax concentration on the height. And now we move to the variation of the temperature, and to do this we wrote heat transfer equation, and here you can see its solution. So we obtain the temperature dependence on the height, and as we know the cooling and dissipation process, we should find the temperature of the wisp, and we can find the temperature of the wick of candle experimentally by thermal camera. Thermal camera cannot show the temperature of the gas, but we obtain from that the temperature of the wick and plot the dependence of the temperature of the wick on the time that we wait after the flame was extinguished. So we evaluate the dependence of the temperature and the wax concentration are high, and can predict a theoretically distance where we can relight our candle. Here you can see the red curve, which is correspond to the temperature of the vapors, and the blue line correspond to the required temperature that we need to relight candle. And we have line, we have region instead of line because required temperature for lighting is not good obtained quantity. So if we wait some seconds, the temperature required for relighting is increasing, and thus we can obtain less height of lighting to be possible. So the intersection of these curves gives us the theoretical answer of our problem, and thus we can move on the theoretical part. And as we did our experiments, first of all we investigate different ways to extinguish our flame. A lot of different ways of extinguished did not give a pronounced wisp of smoke because they closed the way of this wisp. So we understand that the best way is to blow the flame out. And as we provide preliminary experiments, we saw that we should exclude some turbulences around the wisp. And here you can see our experimental setup. We put on lighter on the same way, and we extinguished the flame by the blowing, and after some seconds after it can relight by the lighter put in some height. And here you can see the statistic of relighting, and we understand that if relighting can be obtained only once, it can be not real the maximal distance. So we understand that the maximal distance for this candle is about 19 centimeters. And here you can see the time dependence of the height, which depends on time. We understand that if we put lighter in the a small distance, the wisp needs a few time to upward to this distance. And if we put lighter in the higher distance, the wisp needs more time to go to this height. And here you can see the dependence of the height of the lighting in different parameters. The red line corresponds to the minimum time needed to wisp go upward to the lighter. The green one corresponds to our prediction, our theoretical prediction of relighting to be possible, and the blue one is corresponds to the turbulences in the height of the wisp, which is crushed the steady smoke, and that in turbulence region we cannot relight the candle. And here you can see the same results for other candle. This candle was with thinner wick, and thus we couldn't obtain, it couldn't provide a lot of wisp of smoke. So in this table you can see different candles, and we understand that the most important parameters is the properties of the candle. We investigate different whites of the candles and different times of candle burning, and we understand that increasing of burning time increases the wax concentration of the wicks and leads to growth of maximal distance. And we investigate the dependence of different type of air, and we did this experiment to humid air, and we understand that humid air reduces the maximal height. So in our report in preliminary observation we understand how this phenomenon is work. Then in theoretical part we investigate the dependence, theoretical dependence on maximal height, and in experimental part we proposed our experimental setup, which is extinguished flame very careful without any turbulences and investigate different dependencies on the key parameter. Thank you for your attention.
Okay, so this is our opposition for their presentation on the candle lighting trick. So first, let's start off some good points. They did a nice presentation and theoretical effect. Okay. So they did measurements many times, and they took a lot, and they did a really nice way of extinguishing candle. We liked it a lot that they used that like a pendulum thing that hits a drum and then it blows out the candle. That was excellent to make to have it blown out the same way every time. We like that they actually made a simulation of smoke rising up, but we are not exactly sure how the simulation was made and is it legitimate. So how do we know that simulation has any physical value? How do we know it's realistic? We couldn't really tell, but okay. So they had a nice presentation, and but we think it was presented very quickly, and that the presentation was a bit too long for the 10 minutes mark that they had for presenting. But otherwise, it was very, very good. So these are some points that we should like to point out. Two first presentations, I already said it. So they said that the big problem they had was diffusion. And first of all, can you prove to us that diffusion was really a problem you had here, or that there was something other than diffusion, or if really the diffusion is the problem you had, couldn't you use some kind of like tube to force the smoke into it that would get rid of diffusion? Maybe. That's just one proposition. We have a problem with your experimental method. And that problem is that you didn't vary time of relighting as a parameter. And you stated it was an important parameter, and we believe it also to be a very important parameter. And as I can tell, you had, as you said, you had the lighter on the whole time. So you didn't vary it at all. First time you got in contact with it, it lit. You could have waited a bit longer and get a bit higher result. Or something. You didn't vary it with time at all. You didn't state how did you model that vapor, because the problem is that you don't know the concentration of density depends on concentration of paraffin vapors in air. It's a mixture of air, paraffin vapors, and other particles. And we didn't actually see how did you calculate that density, and also. As the smoke cools, its density also changes and it goes up slower and slower. We're not sure if that is taken into account, and we would like to see if the equations of motion are true to physics. Okay. So we have some questions that we would like to see. Does the width of the candle matter? You found that it is a parameter, so we'd like to ask why. Why we can't relight a candle at certain distance? What is your criterion for not being able to relight the candle? What is the cutoff line? How exactly did you measure that? And and we would like to and connected to that, what exactly is the blue line? How exactly is the blue line calculated? That's the cutoff height. How exactly was it calculated? Like, this is physical motivation for calculation. This is how exactly was it made. And so I would like to probably start with this question. Why can't the candle be relighted at some particular height?
Okay, as we saw in our experiments, we really understand that diffusion and turbulences in the height, in the maximal point of the wisp, is the main problem of the relighting to be possible, and we understand that these turbulences determine the maximum height.
Turbulences.
Turbulences,
and
yes.
how did you
Because
calculate
can I
that?
show you
Yes,
our
please.
video, please?
The reason you cannot relight it is turbulence.
Yes, all parameters.
Can you show that blue line graph again, that where you calculated the max height? And yes,
here?
this. Yeah, this one. And
Yes,
is
this one we obtained from this requirement on.
And how is this related to turbulence?
This line doesn't relate to the turbulences. In the next slides, this blue one relates to the turbulences, and this blue one we obtained from our experiments, and we see that in some height the wisp of smoke become curvy, and in this region smoke couldn't be relighted.
But how do you know it's because of turbulence? Why?
We see it. I will show you now.
How do you know it's not some other parameter and not turbulence?
Look, we did a lot of this video, and we see that if.
But there's no turbulence here.
Yes, here is the distance.
Wait, this was laminar part.
Yes,
That's still later.
This is laminar, and this is the reason why in this height we can relight candle. And if
we hadn't lit it here.
Yes, we did a lot of experiments, and in this experiment we put our lighter in this distance, and in other experiment we put our lighter higher, and if we put it higher, you can see even in this region this wisp is curvy now, and if we put it 2 centimeters higher, wisp would be very curvy and light.
But if you look closely, this part that is going here is not curvy at all. In fact, we found the turbulence is not important parameter.
Yes, look, this region is not curvy at all, and this means that in this region we can relight the candle. And if we go lighter,
but this goes up.
Higher.
It's just a question of time. No?
No.
It goes up.
No, when it go to some height, look, here is wisp is very steady, and in this region is became
let's move on. But can you explain, please, what the blue line then represents, and how is the blue line calculate? How do you
this blue one
theoretically model height?
Theoretically, blue line was.
Yes. What's your theoretical model? How do you get to? What
this
is your
theoretical blue line was obtained from that formula that we obtained from.
But what is it?
This condition to relighting to be possible from the temperature required to relighting and the wax concentration that we related with pressure of wax.
But in the experimental model, you just stated that the turbulence is important, and here you plot.
No, in experimental we also see that green one, which is correspond to the our theoretical. This green one correspond to our theoretical prediction, and we understand that higher that this green region candle cannot be relighted. Okay, this green
so
light is combination of theoretical blue line and theoretical red curve that we studied
So
earlier.
you say time before relighting. It's
Yes.
an important parameter.
No,
time
time before relighting, it is the time necessary to wisp go upward to the height where lighter is pointed. Okay?
Oh, okay.
Look, we here is our candle.
Thank you for your discussion. Now we have to go to the questions from reviewer team.
So can you see the slide with the success rate of the relight?
The success experience.
The success rate, the blue band, not
This one.
Is it when you
This
do
one.
the statistics when one how many
Oh,
times
okay,
the
okay, I
light
understand.
can
Sorry.
go?
This one, yes.
This one.
Yes, okay.
Okay. And the 25 centimeters is that just one time.
Yes.
Good, yeah, this
This was a good experience.
Good. And can you see the theoretical model, please? The theoretical
Okay, of course.
The result of the theoretical model?
This is our condition to relighting to be possible.
Okay.
And to clear, in that experiment data, we combine this blue one and this red one and obtain that green region.
Okay. Any question?
Yes, I have a question. Could you go to the slide with all the curves, the green one, the blue one, and the
Okay.
the number? Already, I didn't understand. Okay, this one. Can you repeat me to understand what represents the blue and the green curve?
Okay. Blue one corresponds to the height where wisp became very curvy because in some height it was steady and then it dispersed and became very curvy. And this blue one we obtained experimentally from our experiment.
Thank you for your explanation.
So is it like a limit?
Yes,
Excuse
it
me,
is.
time is
In the beginning. Then there was a kind of complete theoretical model about how the phenomenon happens with thermodynamical calculation. Then there was also a model in which the maximum height can be computed. There were a lot of confrontation from the between model and experiment. It was presented a simple yet accurate experimental setup in order to study the cutoff length of the phenomena. And also there was a lot of statistical study about this phenomenon. As a drawback, I have to say that the presentation was too fast. And then the opponent focused its first part on the simulation because it was presented a simulation with no theory behind the simulation. So it was simple. Then the role of the turbulence drive the discussion for kind of most of the time about the problem. The flow laminar turbulent. We can discuss about it later. And also no doubt about about the study of the time dependence of the phenomena, because the lighter was turned on all the time. So the doubt of the opponent was about can this permit us to study the time dependence of the phenomena, as stated from the reporter. And also it was pointed out that there was also no study about the power field density. So, to drive the discussion further, we can try to close this discussion about the relevance of the turbulence in this phenomena. And also, we can move on further in studying some parameters that can be modified in order to obtain better experiments. And also, as a last point, we can ask the reporter to bring further the discussion of the simulation in order to clear all the obscure points.
We can start.
I think we can start with the discussion. In trying to end the role of the turbulence with, in a brief way, I would like to have the opinion of both of you. Before, I want to say, well, I want to hear the opinion of the opponent about the role of the turbulence in the phenomena.
We think that turbulence is not relevant, and also their measurements show that, because their like curve they calculate the maximum height based on parameters of relighting of the temperature parameters is all the time below the turbulence part of the graph. Okay, so they
Okay, so this is your
have
argument?
this, yeah. I just say their measurements also confirm
Okay.
that turbulence is not relevant factor.
Okay, so turbulence is not relevant, and the experiments show that. What's the opinion of the reporter on this argument?
When we studied this problem, first of all,
Talk with him, please.
when we studied this problem first of all theoretically, we didn't think that the turbulences is the most important parameter. But when we start to make our experiments with our experiment setup, we see that the wisp of smoke is very steady, but in some region it becomes very curvy, and it's look very good that it is the wisp of smoke very thin, and then it's became big curvy, and this was our the most parameter that candle cannot be relied.
I agree with that, but why is this relevant if you can only relate it here? Why is this line relevant? Okay.
No,
Okay,
in my graph you can see that we have points in this experimental point in this blue line. I can show you.
Okay.
Okay.
So just show it. Let her talk, please.
Okay.
Okay, time is running, so please just show the graph. Then I think we can move on more interesting points that hasn't been covered.
You can see that really we obtain the maximum height. Even the green region is higher, but we obtain the maximum height of 21 centimeters. This black point is our experiment. And we obtain this height due to the turbulences and due to the wisp was very curved in some height.
Last thought on this subject.
Okay, 5 seconds.
Okay, I think that we could explain this data without this blue line, just with this red line, which is the height of the smoke.
No, but
and with this.
But this region, see, but for this region, this red line doesn't matter because this red line corresponds to the time needed that wisp go upward to the lighter. And in this region, after 1.5 seconds, this is not necessary to wisp already come to the lighter.
Okay, time is running.
Sorry.
Can I have some opinion on parameters about that can get the experimental stuff better? Opinion of the opponent?
Okay, so
50
we
seconds.
think we think the most important parameter is
That can be changed.
Yes, time after lighting and wick diameter of the wick, because diameter of the wick.
Okay, it's time for the reporter to go.
Okay, I think that the diameter of the wick is.
Can you
important.
improve your experimental
Okay,
problems?
my experimental
No.
problems.
I'm sorry,
Their opponent says that we should point lighter after the flame was blown out, and we think that if we wait some seconds.
To cut off because
Can I answer, please?
yeah, but hurry up.
A short answer, okay? I understand that if you wait some seconds, the wisp of smoke, the concentration of the wisp would be less than if we wouldn't wait. And we understand that if we have maximal concentration, we have the maximal distance to lighting, and then we put our lighter on the same distance and didn't move on later.
Okay, question from...
Can you please turn on the slide where you calculate heat equation, like differential equation, it's somewhere before. Wait, you skipped it.
I would just like to say that I think
Yeah, 1 second.
The transfer equation.
Is
What
my
does it
question.
describe? The wick or the smoke?
This is wisp of smoke.
Smoke.
Yes, yes.
But this equation doesn't have dependence on the z-axis, and that doesn't make sense because
yes, we calculated with Wolfram.
that means
Wolfram
that
Mathematica.
that means that the temperature doesn't
We
depend
calculate
on the
with the
z-axis.
Wolfram Mathematica, obtain the dependence, and then we obtain, here you can show the dependence of the height z.
Can
We
you-
obtain this. From this solution, we obtain the dependence on the height z, and you can see it in the same slide.
but the equation didn't have z.
It's z independent.
I can answer this question. We substituted the dependence on z with time dependence. We considered the velocity with which the wax vapors move. It was shown down there, like t from z is equal to initial position minus the velocity of the vapor flows times
How did you
time.
obtain that? The z dependence. Where does it come from?
We consider the flows of the vapor to be with constant velocity,
Okay.
and we just multiply it by
What
time.
is your model of cooling?
Cooling. How does it
Cool-
cool? It decreases temperature.
Hey, 1
decreases
second,
with
no,
time.
no double attacks, please. He's asking the question. So,
I mean, how does it cool? Where does it come from? Why?
We understand that if it's higher is the point of the wisp, it is cooler, and we obtain we obtain the solution of this equation from the
I mean,
From the-
it's linear dependence. I just asked where does the linearity come from?
mathematical. Want to say something?
And like here,
Okay.
it's directly connected to our simulation we performed, and like I need to like verify what it was. It's a secret 2007 paper to modeling of the liquids and the fluids, and they also consider the smoke simulation, in which they consider the convective flows of the smoke, the buoyancy force, the diffusion, the heat transfer, and the vorticity confinement.
Okay, then for how long does this equation hold? Because it's, after some time it should reach 0 Kelvin, so that doesn't really... It would make more sense to be exponential or something. This is constantly decreasing. So it's...
We
Yes,
studied for
if-
just
if
1 second, calm down. One person answer to the question,
If we go
and before asking the
in
word.
the maximum height from the candle, we of course obtain the temperature of the air in the room, and you can see it here.
Okay, is there another question?
I want to ask you
You
that
can ask.
indeed this formula works when our flux is laminar, and when it becomes turbulent we cannot use this formula, and we are not interested in situation in turbulence here.
Okay.
To answer the question about the influence of turbulence, in simulation it was considered as a vorticity confinement at which the vortices are generated.
Talk to the opponent, please.
Like, just explaining. The vortices are generated within the smoke, and during this process the concentration reduces significantly then from just the laminar flow of the vapors. So that's important to determine the maximum possible.
Okay, I'm sorry,
Thank you.
but time is up.
Thank you. Now the concluding remarks by reporter.
Okay, the problem asks us to study the maximal possible height of relight in the candle, and we investigated theoretically, and then we verify it experimentally. We use a lot of candles that we can find, and we obtain the maximum height about 21 centimeters, and we think that we can obtain more height by using the thicker wick of the candle. And I think that we provide good experimental stuff which allowed us obtain results free of human factor and very repeatable. Thank you for it.
Now it's time for questions from the jury. Please.
So you have done theory that was really fast, so I also did not understand everything, but then you have some comparison with the experiments, and as I understand, the red and the green curves are comparisons with theory and experiment, yes? In your main curve with the red
yes.
and the green?
No,
No?
No.
No?
Their green curve correspond to our theory prediction
Yes.
of the maximal height.
Yeah.
And
Yeah, that's the green one is theoretical.
the red line correspond to the minimum time needed to...
Okay. So let's go for the green curve then.
Okay.
So the formula that gives you the green curves, solving some differential equation and something else, it contains a lot of physical parameters.
Yes.
How were these parameters obtained? How did you get the numerical values for those?
So we obtained, for example, temperature of burning reaction from the literature, and this is the reason why we obtained not the line, but the region of this, because
Which other parameters were in there? Which parameters? Did
temperature, pressure, molar mass of the piece. They all was in our formula. I can
It depends on
forgot
the
something.
heat capacity, on the energy the temperature required to start the
Okay,
ignition.
and you found all those from literature?
Yeah, there was like the condition for it to occur, and there was
but
a
you
couple
didn't
of
measure
parameters.
them.
The value?
Yeah.
No, we found it from the literature. And
Yes, it was
we
obtained
only measured the concentration of the wax from our simulation, and thus obtained the pressure.
Okay, I have a small question. As you stated, the main reason of losing possibility to relight the wax is the turbulence.
It seems to us.
And okay, your theory corresponds rather well, I think, to your experiment. And is there any criterion that you use it to, any numerical criterion, to predict that the turbulence will appear and it will, and the possibility to relight the candle will be lost? Because I have
Only experimental, yes?
only experimental. Experimental is just like observation.
Yes.
I can add from simulation we are able to determine the distance at which the vorticities form, and we can observe the turbulence.
That wax
And that's
simulation
the
of
only
wax
way we can do this
concentration
theoretically.
allowed us to obtain this.
Had you
But it
tried
was-
probably to estimate the relay number?
No, we didn't estimate, but because we obtained it from our simulation, and we saw a good agreement, and we understand it. And we didn't investigate it more because we see it by our eyes in our experiments.
Thank you. Alexei?
The question corresponds to Vladimir's question. I have understood that your limitation in your theory and in your observations is turbulence flow.
No, we have a lot of limitations.
Blue
For example, for this region, the main reason is the turbulence.
Yes, and
but
that-
if we weigh something,
only on the maximum height. Yeah, is your limitation is turbulence flow. Okay, if I put your tube and there is where there is no
okay,
turbulence
I
flow,
understand. Of course,
is the maximum height higher?
of course, it would be higher because in one experiment we observed the distance not 21 but 21 centimeters, but it can be very, very high because the wisp of smoke really cooling, and in some height we cannot relight it because wisp of smoke would be cold and cannot relight it.
And in this case, the limitations would be temperature.
Of course, yes, would be temperature. And if we find
I see.
the
Okay.
Another question, please.
So, I would like to ask the visitor, you talked about a lot about the diffusion process. So, when you're trying to resolve this problem, did your team try to light after the diffusion started?
No, we think diffusion, we tried putting it in the tube, so diffusion wasn't a problem for us. But when it wasn't in the tube, the height at which we could relight it was lower than the height at which where the diffusion seems relevant. So we think that diffusion isn't important because of temperature you lose the ability to light it before the diffusion takes place, just like we see in this graph. Because
Yes,
this green is...
yes, it's for longer time, but if we want to obtain the maximum height and it is in this region, and we see that green line is higher and blue one is lower.
But if you take the middle,
Can I see about something?
So maybe another questions, we have not so much time.
Oh, very quickly, what would be the origin of the instability?
Reason of instability, diffusion in the wisp, in the some height wisp became curvy and disperses due to diffusion.
Why? Why is it like occurs? Because if it's just diffusion, it should be like you said, linear. But at one point in the videos, we see that it's
maybe between the two folds of the vapor and of the air, there is a Kelvin-Helmholtz instability on the boundary. So it may cause the turbulent flows and the mixing of the vapor, and so the concentration decreases and we cannot relight in a molecule.
Thank you.